Sup, y'all? So in our next video, we're going to be looking at the general form of our energy conservation equation. Now, we've actually kind of used this, right? We've defined work to be the change in energy of our system. When work is done on the system, it either gains energy or it loses energy, right? So really, we've used this, we just haven't written it out formally like this. So I want to present it to you, and then I want to show you how we can use this by looking at one of the rides that I grew up seeing at Six Flags Astroworld, which is the Skyscreamer. All right? So this is the equation right here. The equation is that the amount of work done on a system is equal to the change in the kinetic energy plus the change in the gravitational potential energy plus the change in the elastic potential energy. Now, you could add other types of energies on here, rotational kinetic energy and whatever else you want to put in there, but these are the three that we've looked at up to this point. Okay, so don't be surprised someday when they start adding other terms on here, because this is just limited to what we've been doing right now. But this will be limited to taking either work out or putting work in, which will be equal to the change in energy of the system. All right, so we're going to talk about the Skyscreamer today. The Skyscreamer was a ride. It was a drop ride, kind of like the Zumanjaro Drop of Doom, except it wasn't quite as high. It was probably about 40 meters high, maybe. I think it was probably 7 or 8 stories, and it would take you up, and then it would drop you, and as it dropped you, it would drop straight down for a little while, and then it would curve, and then you'd be laying on your back until you got to the end. Now, the Skyscreamer did use friction at the end, or maybe some magnets there as well to slow you down at the end. I'm going to use a spring instead, just because I want to be able to connect it to the elastic potential energy as well. But the way the Skyscreamer worked is you'd get to the end, and then it would flip you back up, and then you'd get out, and the next ride would go. And that's basically it. So I've put some basic information here. This isn't exactly like the Skyscreamer, but it's close enough that we'll be able to understand what's going on. Okay, we've got that the box itself, the ride itself, has about 800 kilograms of mass. That's when the people are inside of it. It's about 40 meters off the ground. And then as the ride comes down and slows down as it hits the spring, it's going to be about 2 meters off the ground. And that's going to be important here in just a little bit. All right, so we're going to look at two different things here. First thing we're going to look at is what happens as the ride goes from right up here. So we're going to start at the top, and it's going to go down, and we're going to find out how fast it's going when it gets to the bottom of the ride. Now, we are going to assume no friction. Obviously, if there was friction involved, this would change the question. Energy would be lost. But in this situation, we're just going to say there is no friction, no energy is being lost. The only force that we'll look at is the force of gravity. We've got the force of the track, which is a normal force. That's always going to be perpendicular. And remember, we said perpendicular forces don't do work. And then, of course, we'll have the ride hitting the spring later. But we're going to be considering the ride, earth, spring system. So hitting the spring would lead us to have elastic potential energy, and that force is internal. That force would be between the spring and the ride, and so we won't need to include that as an external force. All right, so we're going to start here, and we're going to end right down here when it gets to its maximum speed before it hits the spring there. All right, so what we're going to do is we're going to use this equation. The work equals change in kinetic, change in gravitational potential energy, change in elastic potential energy. We're going to write that out. So we go work equals the change in kinetic plus the change in gravitational potential plus the change in elastic potential. Now, before we just start willy-nilly throwing some numbers in, what we want to do is we want to identify when does it have certain types of energy. We also want to identify, is there work being done? We already talked about the fact that there's no friction. There is a perpendicular force of the normal, of the kind of the rack, the ride there, the track. So we don't have to worry about that because it's perpendicular. And therefore, there is no work being done. So we're going to say 0 work. Now I'm going to break this up so that it's kinetic final minus kinetic initial. All right? Kinetic final minus kinetic initial. That's what the change in kinetic energy is. I'm going to have the change in gravitational, which is the gravitational potential final minus the gravitational potential initial. And then at the end, I could have the elastic potential energy. But for this situation, if I'm starting up here at the top of the ride and I'm ending right here at the bottom before it hits the spring, the ride hasn't interacted with the spring yet, so I don't need the elastic potential energy. So we can actually just say, we're going to take that guy out for this first situation. Okay? Now, what else is zero? Is there anything else that we can take out before we start willy-nilly putting some numbers in there? Okay? Well, we know that the initial kinetic energy is zero. It starts at rest before it gets dropped, right? So that initial kinetic energy is going to be zero. So we're going to take that guy out. Always pay attention to the minuses, but it's going to be minus zero, so that's going to go away. Now, the other thing that we can do is something we haven't really talked about too much yet. We can define where zero height is. All right? You could make the very bottom be zero, the ground. Okay? So you could say that at the end it's 2 meters off the ground, and in the beginning it's 40 meters off the ground. But sometimes it pays to simplify a little bit. I can actually define this as being zero. So if I define that as height equals zero, then what that means is that my final gravitational potential energy will be zero, because the height is zero there. And don't get too worried about it, because really, remember what we're going to be finding is the change in the gravitational potential energy. So I can make zero wherever I want it to be. I could make that zero, and then I can make this a negative height. But people don't usually like negatives. So I'm just going to make the bottom of the ride here be height equals zero, which means that I'm not going to have any final gravitational potential energy. Okay? Now I'm going to go ahead and start putting numbers in. I've got the zero. It's going to be equal to the final kinetic energy, which is going to be 1/2 times the mass, which was 800, times v squared. And then that goes away, that goes away. I've got minus the initial gravitational potential energy, which will be the mass, times g, which is 9.8, times the height. But remember, the height is going to be from the zero that I just defined, which was 2 meters up. So I'm not going to put 40. I'm going to put how high is this compared to my new zero, right? So this was 2 down here, and so therefore it's only going to be 38 above where it ended. All right? Now you may say, well, isn't that more work than before, because now I got to subtract? In some cases, maybe. My goal here is to show you that it works. Then you can make the decision of, do I want to identify specific places as zero, or do I just want to count the ground as zero? In some cases, you won't know how far it's off the ground. And so by creating a new place where it's zero, it actually simplifies things for you. Okay? So again, just showing you that it works. Now at this point, we should be able to solve. All right? So I'm going to go ahead and speed up that part, because you can do the algebra. If not, go in and check with me later. All right, so here we go, algebra. And I get 27.3 meters per second. So I was able to figure out the maximum speed before it hit the spring. Okay, no problem. Got it. All right, now, that showed something we've seen before, right? Turning that gravitational potential energy into the kinetic energy. What I want to do next is we're going to find out, what does the spring constant of a spring at the end need to be if the spring is only allowed to compress 2 meters? How stiff does that spring need to be to stop the ride and bring it to rest? All right, so that's going to be our next step. Okay, so we're going to erase what we got there, so we got some more space, and here we go. Now here's the neat thing. We actually have 2 choices, because energy is conserved for this whole thing. There's no place where external forces are occurring. There's no place where energy is going to be lost due to two objects running into each other. As long as this is what we call an ideal spring, which is all we're going to do in this class is ideal springs, which means we're not going to lose energy anywhere. So you have two choices. You can either say, I'm going to start here, and that energy is going to turn into kinetic energy, and then it's going to hit the spring, which is then going to turn into elastic potential energy. So you can do your second spot there where it hits the spring. Or you can use the information that you got last time, and you can say, well, I'm not going to start here. I'm going to start with my kinetic energy right before it hits the spring, and then say that energy is conserved as it hits the spring. And again, the second place will be here. Now, because I want to show you that it can be done, we're going to go ahead and start up there at the top. All right, so that's what we're going to do in our next step. We're going to use the same equation. I want you to show that we can use that same equation in order to solve for how far is the spring going to compress. All right, so we'll go ahead and write that out. Change in kinetic plus change in gravitational potential plus the change in elastic. All right, that's what we're going to start with. Now, again, we want to talk about, is work being done? Well, we said no. No work's being done because we're going to look at the ride, earth, spring system. The only other forces are either perpendicular, like the normal force, or there just aren't any other forces. We said there's no friction. So therefore, no work being done. So work is going to be 0. Now this is an interesting situation. We now look at the kinetic energy. How much kinetic energy does it have at the beginning before it drops? 0, right? And then, how much kinetic energy does it have when it compresses the spring? Comes to rest, doesn't it? Okay, so it has 0 at the beginning and 0 at the end, which means there's no change in kinetic energy. Okay, you don't have to worry about the fact that there's kinetic energy in the middle because energy is conserved throughout. So yeah, when we looked at the blocks, yeah, some of that gravitational potential energy is going to move over to the kinetic, but then I'm going to take that kinetic and move it right over to the elastic potential. And so in the middle, it doesn't matter that there's kinetic energy. What matters is that I have the same amount of energy in the beginning and in the end. And so the kinetic here is going to go away. All right, we definitely have a change in height, so we definitely have some gravitational potential, and we definitely have some compressing of the spring here at the end, so we're going to need that guy as well. Okay, so we're going to go ahead and add in, we're going to go gravitational potential final minus gravitational potential initial plus, again, the change in the elastic potential final minus the elastic potential initial. And we add all those together. All right. Now, are any of those going to be 0? Well, we have the elastic potential final, right? The elastic potential final, that's when it's down here. If we use this H0 again, that means that my gravitational potential energy final is going to be 0 because I'm going to be down at what I've defined as 0. MGH, H is 0, MGH is 0. The initial gravitational potential energy is this up here. So I definitely have that. There's definitely some height going up there. All right. The elastic potential energy final, yep, I got that. That's right here. That's going to be stored when I compress the spring and it comes to rest. Elastic potential initial, well, that's when the ride's up here, the spring hasn't been interacted with. Remember, potential energy requires that interaction to take place. So no elastic potential initial. Now we can just plug in the numbers, right? All right, let's do it. So we put the 0 equals, that guy's gone. I do need that negative there. Then it's going to be the mass, which was 800. This is mgh, right? So m times g, which is 9.8, times h, which is the height. But remember, that's the height from 0, which is here. And so the height from 40 down to that 2, that would be 38. So we put in that 38 here. And then we're going to go plus the elastic potential energy, which is 1/2 kx squared. And I did say earlier that I wanted the spring to compress a total of 2 meters. I don't know how long it was initially. I don't know how long it is finally, but I do know that the change is going to be 2 meters. That's how much distance we have in order to stop this Skyscreamer here. So we'll put that 2 in. Everything's in SI units. That's why I didn't include my units here. Now we should just be able to go ahead and calculate. So at this point, it's algebra. Let's speed through. And there we go. We ended up getting that K must be about 150,000 newtons per meter. Okay, 148,960. All right, and that's it. You've been able to solve for that. Now, if you want, go ahead and see if you can do the same thing by doing conservation of energy starting here when it had kinetic energy that we solved for in the first question. And then at this point, once the spring is compressed, see if you get the same thing. You should still get that K needs to be about this number. All right? Perfect. I'll see you next time.